So we're going to keep talking about inner products and stuff, inner product spaces. And just a reminder, the last thing that we talked about on Tuesday, I guess it was, is this thing called the closest point theorem, right? So the closest point theorem answers the following question. If you've got some vector space V, and you pick some subspace W, and you specify some point B that could be in W, but then the question's boring, so let's assume it's outside W. Then the question that you want to ask is, what point in W is as close as possible to B? What's the closest point in W to B? And the answer is, it's the projection of B onto W. Okay? So we've answered the closest point problem. Now we want to apply this idea to something extremely practical. Okay, so now we're thinking about the following problem. So now suppose we've got some linear system, Ax equals B, right? And I'm going to make this even more practical in a minute by talking about what particular linear system you might be interested in. That's going to be related to data fitting and stuff like that. Well, let's just say we've got some linear system that we're interested in, right? It's got m equations, it's got n variables, and what we're interested in doing is finding some x that minimizes the distance between Ax and B. Now, why might we be interested in doing that? Well, what's the simplest possible scenario here? If you're interested in the linear system Ax equals B, what's the best case scenario if you want something that minimizes the distance between Ax and B? Yeah. If your system has a solution, you just pick x to be a solution, and then Ax equals B, and then the distance between Ax and B is 0, right? So that's the best case scenario. If your system actually has a solution, then the answer to this problem is easy. You just pick a solution. The reason this is an interesting problem is that very often, particularly in applications, you'll have a linear system that you would like to be able to solve, but that system doesn't have any solutions, right? Now, that doesn't mean that the equation you started with is stupid and you should throw it out and go do something else. What it means is you've got to find the next best thing. And the next best thing is, all right, there's no x's that actually satisfy Ax equals B, but let's pick an x that makes Ax as close to B as possible. Okay? That's a pretty sensible thing to do. If your system doesn't have any solutions, you just pick an x that's as close as possible to being a solution. And this is what we call a least squared solution. Okay? And it's called least squares because if you think about what this distance looks like, if you square it at least, get rid of the square root, it's just the sum of the squares of all the differences between the individual coordinates, right? So it's b1 minus ax1 squared plus b2 minus ax2 squared, right? So it's the sum of all the squared differences. And what we're trying to do is pick x to minimize this sum of the squared errors, right? So that's why it's called least squares. This idea is now extremely widely used. I think, I'm not an historian, I think this goes back to Gauss actually, and I think amongst all the other amazing things Gauss did 200 years ago or whatever, he came up with this idea, and this isn't, something that was his favorite achievement, but he managed to predict something, and I should have looked this up, predicting where this lost comet had been, that astronomers didn't know why it had disappeared and when it was going to reappear. And he said, all right, using this least squared stuff, you wait a month or so, it'll be over there. And then the astronomers waited a month, and it was, lo and behold, exactly where he said it was. So that's sort of how, even though this is probably not his greatest achievement, this is really one reason he became very famous very quickly. Okay, So let's get into it. So we want to try and understand properties of these x's that minimize the distance between ax equals b. So ax and b. All right, so the first characterization we have is, I think, probably the most insightful, but not the most useful, but it is going to be an ingredient in helping us produce something that's a really useful practical tool for finding these x's. But what the following theorem says is that pick W to be the column space, right? So we know this, why is the column space coming into it? Column space is coming into it because we know ax equals b is going to have a solution if and only if b is in the column space. Right? B is not in the column space, ax equals b doesn't have any solutions. So what we're going to do is, all right, if our right-hand side isn't in the column space, we're just going to project it down onto the column space. Okay? And then so what we're effectively doing is replacing the right-hand side with the closest thing in the column space to what we want the right-hand side to be. Okay? And we know if we do that, then the resulting equation, this thing, that's definitely going to have a solution because the projection of b onto the column space lives in the column space. And so now you've got an equation where the right-hand side lives in the column space, so it's going to have solutions. Okay? So this is a fairly sensible thing to do. And the claim is that x is a least squared solution of this thing, the equation you're actually interested in, meaning that it minimizes this distance between b and ax. It's a least squared solution to the thing you're interested in if and only if it's a genuine garden variety solution to this new one, where you've replaced b with its projection onto the column space. Okay, does this sound like a plausible thing to be true? All right, so let's prove this. So by definition, x is a least squares solution of ax equals b if and only if x minimizes the distance between ax and b. Now, for any x in Rn, what do we know? We know Ax lives in the column space, which is what we're calling W. Okay? So no matter what x is, Ax always lives in the column space. So let's go back. We need, I think, theorem 741. Let's remind ourselves again. The closest point in W is going to be the projection. All right? The closest point to B in W is the projection of B onto W. So theorem 741 tells us that the projection of B onto W is the closest point in W to B. Right? So if we want AX to be as close as possible to B, we have to choose AX to be the projection of B onto W, or B onto the column space. Okay? You don't have any choice. There's only one thing you can demand AX is going to be if you want AX to be as close as possible to B. Because AX lives in the column space, and the closest point in the column space to B is the projection of B onto the column space. That's the whole argument. Now, the interesting thing here is that even though this closest point is unique, right? There's a unique point in the column space that's as close as possible to B. There could be lots of x's that produce that, right? There could be multiple x's such that AX equals this projection. There's no uniqueness in x necessarily, but there is uniqueness in the closest point problem. So there's one correct right-hand side to replace your right-hand side with. You start off with B, you should replace it with a projection of B onto the column space. But then there could be lots of solutions to AX equals the projection. Okay, so what are we saying? The distance between B and AX, because AX lives in the column space, it's going to be minimal if and only if X is such that AX equals the projection. Okay. Let's do a quick poll, see if we've got a head around this. All right, so true or false? So we know linear systems don't always have solutions, but does a linear system always have at least one least squared solution? Can you think of a linear system that's not going to have any least squared solutions? Okay, so does a linear system always have to have at least one least squared solution? How many we got? 1, 2, 3. Okay, about half of you haven't done anything, so I'll give you another 10 seconds. Okay, so let's go back and look at what we just proved, right? So AX equals B. Well, X is a least squared solution of AX equals B if and only if it's an actual solution of this equation. That second equation always has solutions, right? Because the projection lives in the column space, so it's consistent. So that second equation always has solutions. There always exists X that satisfy that equation. Therefore, there are always X that are least squared solutions to the first equation. Okay? So what we just showed tells us the answer to this is true. Okay? So this is good news. Not all linear systems have solutions, but at the very least, all linear systems have least squared solutions. Okay? So you can always answer the question, well, if there aren't any solutions, what's the next best thing? You can always answer that question. Okay, so is there a way of doing all this searching for least squared solutions that doesn't involve abstract weird stuff like the projection? And the answer is yes, and the answer to that is given by this following theorem, which uses this thing called the normal system. Now, I honestly have no idea why this is called the normal system. It doesn't seem like a very good name, but that's what it's called. And what this system, well, the point of this system is that if you're interested in AX equals B, then x is a least squared solution to ax equals b if and only if it's an actual solution to this thing. Okay, so part of this theorem is that this normal system is always consistent. Okay, so you start off with any A at all, doesn't matter how horrible it is. You take A transpose A, and you take A transpose B, and you try and solve that corresponding linear system. That thing has solutions. Okay, so somehow multiplying your original equation by A transpose forces it to be consistent. So why would that be the case? Okay, let's have a look. So, once you know this theorem is true, you can stop thinking about projections, but we need to think about the projections to prove this theorem. 744, I think it was. Is that what we just proved? Yep. Okay, so 744 implies x is a least squares solution of ax equals b if and only if it's an actual solution to ax equals the projection of b onto the column space. Okay, so I'm just going to prove one direction here. You can prove the other direction on the problem set, right? This is an if and only if, so we need to prove both directions. So if ax equals the projection onto the column space, meaning x is a least squared solution, now we're going to show that it satisfies the normal equations. Okay? So if x is a least squared solution, then what we want to do is understand why x has to satisfy that. Okay, so let's rearrange this just briefly. This is really saying that if you multiply b minus ax by A transpose, you get 0. That's what it's really saying. Now, so let's try and understand what this b minus ax thing looks like. So we know ax lives in the column space. And we're assuming, right, we're assuming that, not that we're talking about b minus ax, we're assuming x satisfies this equation. Okay? So we're assuming ax satisfies that equation. So ax is the projection. Okay? Now, what space does this live in? The projection lives in the column space. Sorry? Say it again.
Column of A.
Column of A. So this part lives in the column space of A. But what about this part? Yes. Right? So why?
Because it should be the perp space of column A, and the perp space of column A is the co-kernel.
That's right. So we're going to use the projection theorem again. So this is precisely in the perp of the column space by the projection theorem. 7, 3, 7. Okay? So the projection of B onto the column space lives in the column space. B minus that, we proved, lives in the perp of the column space. Right? This is just a special case of the projection theorem. right? So if you've got B minus projection onto any space, that lives in the perp of whatever space you're projecting B onto, okay? So this difference, because of the projection theorem, straight from the projection theorem, no tricks, lives in the perp of the column space. But the perp of the column space, we know, is the null space of A transpose. This was theorem 4, 7, 10, I think. You can double check. So B minus AX lives in the null space of A transpose. And what does that mean? It means, just by definition of null space, if I hit B minus AX with A transpose, I get 0. And I rearrange that, and I've got precisely the normal equations. Okay, so the first time you stare at the normal equations, you think to yourself, what on earth has A transpose got to do with anything? But the point is that your least squares solution, if and only if you satisfy AX equals the projection onto the column space, and the A transpose comes in just because the null space of A transpose is the perp of the column space, using the projection, and then applying the projection theorem. Okay? So there's a perfectly natural reason why the transpose comes in, and it's precisely because of this equality here between those two spaces. Okay? So here's a really practical application of why it's useful to know all this stuff about co-kernels being the perps of column spaces and stuff. So now we've got a very concrete characterization of how to solve a least squares problem. Okay, so every least squares problem is a solution to the normal equations. So I'll let you prove the converse, that every solution to the normal equations is a least squared solution. That's similar, but actually a little bit easier. But the last thing I want to show is that the normal system is always consistent. So what we've shown is that if you're a least squared solution, you're a solution to the normal equations. But we know that least squared solutions always exist, right? Just because the projection of B under the column space lives in the column space. So if you look at the equation AX equals the projection, that is consistent because the right-hand side lives in the column space. Right? So there do exist solutions to that equation, and we've just shown that if you're a solution to that equation, you're a solution to the normal equations. Therefore, there do exist solutions to the normal equations, right? Just go find some solution of this. Such a thing has to exist. It is a solution of the normal equations. All right, so the normal equations are consistent. Okay, so other direction on problem set. So I guess in principle, the other direction is the more interesting direction, right? Because then that gives you a recipe for at least finding one least squared solution. It's a little bit easier to prove, so I'll leave it for you to do. But it's good to have both directions because what the direction we've proved shows you is that there aren't any other ones, right? So you go and solve the normal equations. There aren't some least square solutions you haven't found. You'll have found all of them. Okay, so what you should really be picturing when you think of least squared solutions is solutions to this thing, okay? Right? You need to know how to find least squared solutions. And the answer is you solve normal equations. Okay, so let's do an example. So let's find all the least squared solutions of AX equals B when A is this thing and B is that thing. All right, and you can check this system is not consistent, right? So there aren't any actual solutions. So how do we find the least squared solutions? We just construct the normal equations. So we want to solve A transpose A, X equals A transpose B. So we need to find A transpose A. And if you crunch this out, you observe that. And A transpose B, you get 14, 12. Now, what's one property you notice of A transpose A here? This will be important later.
The columns in the right is 3 times of the entries in the column 1. Right?
So the
The column
3 times, yeah, that's probably, that looks true. So that's, I think, a quirk of this particular matrix. What's something even more basic? What's one very generic sort of property this guy has?
Things like this 242, so things on diagonal the same, on the opposite diagonal.
Yeah, so what's that, what do we call matrix? So basically, what does it mean that these two diagonals are the same? What property does it mean the matrix has? It's symmetric, right? You swap the rows and the columns, you've got the same matrix. And you can see, right, that this is always going to hold. Because if I take the transpose of A transpose A, I get A transpose transpose, which is A transpose A. So your A transpose A thing is always going to be symmetric. And that actually has really important properties that we'll talk about next week. But let's just observe that here. So we want to solve this equation. So now this is just, first year Gaussian elimination. You row reduce it, put it in echelon form. In this particular case, we find, even though it's a 2x2 system, we only have one pivot. So there's going to be a free variable. So we've got, here's an example where we have infinitely many least squared solutions. And so everything that looks like this, no matter what alpha is a least square solution. Okay? So you just find that by back substitution. I'll let you fill in the few steps there. But this might seem a little bit strange. Let's think about what AX is. Right? What this needs to satisfy is that no matter what we choose alpha to be, AX has got to be exactly the same distance to B. Right? Otherwise, some of these x's would be such that AX was closer to B than others, and then they couldn't all be least squared solutions. Right? So all of these x's have got to be such that AX has precisely the same distance to B. And if you crunch that out, you find that the alpha thing vanishes, and the alpha thing is always going to have to vanish because whenever we solve one of these linear systems, the bits that have the free variables sitting in front of them are solutions to the homogeneous equation. All right? So when you go and hit this thing with A, that piece that's being multiplied by alpha, it disappears anyway. Okay? So this is why we don't get some kind of contradiction here, having infinitely many solutions, because all these x's give the same AX. All right? And so AX minus b. In this particular case, you crunch it out, it has length square root of 6 on 7. So all the least squares solutions have the same error. All right, so the error is just the name that we give to the distance between AX and B, right? If we actually had a perfect solution, a real solution, a genuine solution, AX minus B would be 0, so the length here of AX minus B would be 0, but the system wasn't consistent, so that's impossible. But the best x's you can pick are such that AX minus B has length root of 6 on 7. Okay, is that kind of general recipe clear enough? How to solve normal equations, how to find errors? All right, this is 100% something I want you to know how to do before you go into the exam. Okay, so this A transpose A thing popped up in the normal equations, and the normal equations characterize least squared solutions, and I'm claiming least squared solutions are important. So this A transpose A thing is probably important, and in fact it really is. And we'll use it again for sort of different reasons next week. So it gets a name. It's called the Gramian. So if you take any matrix at all A, you can consider it's Gramian, and that thing is just A transpose A. And it's a square matrix. Okay? If A is n by n, then A transpose A is n by n. So it's a square matrix. It's going to be symmetric. It's kind of a nice matrix. And here's 3 properties about it. So the first one is not at all obvious, but it is very important. And it's saying that the null space of the Gramian is the same as the null space of A. Okay? The null space of the Gramian is the same as the null space of A. Now, if that's true, then by the rank nullity theorem, you immediately get that the ranks of the Gramian and the original matrix have to be the same, right? Because the nullities have to be the same from here, and they both got to add to n. So I'll leave these for the problem set. If I can remember how to spell and write problem set. But let's prove this one. So the last statement is that the Gramian is invertible, right? And it makes sense to ask whether the Gramian is invertible because it's square. The Gramian is invertible if and only if A has independent columns. Okay? So there's a way of telling whether the Gramian is invertible by just looking at the columns of A. And this may seem like a weird abstract thing, but it's actually really useful for applications. So let's say A looks like this, right? It's something with n columns. So let's say it looks like that. And as we said, the Gramian is n by n. And so it's a square matrix. So theorem 157 says Gramian is invertible. Remember, we've got lots of characterizations of invertibility, but I think the one that we've used most often is talking about the size of the null space. So whether or not your homogeneous equation has non-trivial solutions. So the Gram matrix is invertible if and only if its homogeneous equation doesn't have any non-trivial solutions. Okay, so A transpose A is invertible if and only if the null space of A transpose A is just 0, right? So this is really just the same thing as the last statement, just using the definition of what null space actually means. But by part A, the null space of the Gramian is just the null space of A. So the Gramian is invertible if and only if using part A, right? And this is not trivial, you've got to prove part A, but once we know part A is true, the Gramian is invertible if and only if the null space of A is trivial. Now, what does the null space of A actually, what does that actually mean? Well, this means that AX equals 0 if and only if X is 0, right? But what's our favourite way of interpreting what AX means? What's AX? I started asking this in week 1. Can somebody? Yeah. Yeah. Of the columns. That's right. Right. So AX is the linear combination of the columns of A, where you're picking the scalars from X. Okay. So, what's AX being 0 mean? It means that this linear combination is 0 if and only if X is 0. So stare at that. What does that tell you about the collection of vectors A1, A2, blah, 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 up to AN? Tells you they're independent. Okay? It's precisely the statement that these things are independent, by definition of independence. So the columns of A are independent. All right, and that's the whole argument. And we've actually done both directions all at once, right? Because all of these statements are if and only ifs. Okay, so is everybody with me? So the Gramian's invertible if and only if A has independent columns. Any questions about the proof? Okay. All right, time for another poll, and then we'll put this to use. So, true or false? If a matrix is invertible, a matrix is invertible if and only if its Gramian is invertible. And let me start that one. Okay, this looks like it was a good one to ask. So let's go back and think about what this theorem was saying. So this theorem is talking about any m by n matrix. Right? Now, I can pick a 1 by 17 matrix. Actually, can I? No. I can I can pick a 17 by 2 matrix where the columns are independent. But that matrix is not going to be invertible because it's not even square. Right? It's got independent columns, so its Gramian is invertible, but it doesn't even make sense to ask if it's invertible because it's not square. Okay, so if A is square, the statement's true. But A is not going to be square in general. So, someone will yell at me. Someone not listening to the lecture on the recording who just saw me circle that will yell at me because they put the wrong answer into the poll. But anyway, the answer is false, right? Because A doesn't have to be square. Okay. So let's actually put this to some use now in the last 10 minutes. All right. So why would you want to actually solve these least squares problem in the real world? And here is basically the answer. So let's say you're trying to, this is the simplest possible setting. You can generalize the heck out of this. But here's the simplest possible setting, right? You think some quantity, like say, I don't know, pressure should depend linearly on temperature, right? And it does, at least for simple systems. But suppose that's your hunch, and you want to test this numerically, experimentally, and also you want to find out what kind of straight line does it actually obey, right? So you think your quantity you want to measure is controlled by the thing that you can control. So say you can control the temperature using the thermostat on your wall, and you want to measure pressure using a barometer or something. You would like to check whether or not the data actually do lie on a straight line, and also, assuming they do, you want to find the A and the B. So how would you do that? Well, you do a bunch of measurements, right? Run a bunch of experiments. So you pick the temperature to be 5, and then you measure the pressure, and then you pick the temperature to be 10, and then you measure the pressure, and then you pick the temperature to be 30, and you measure the pressure, blah, blah, blah. Right? So you get all of these data points. You want to find A and B. So how are you going to find A and B? Well, you just pretend like all of the data fits on a straight line, because that's what you think should be the case. So if you stick your data in your first data point, x1, y1, into your equation, you get that. If you stick your second data point into your equation, you get that. If you stick your last data point into your equation, you get that. Okay? Now, we've got n equations, and we've only got 2 variables. So even if you're right? Even if you're right that nature works like this, that pressure is proportional to temperature, it would be an absolute, if you've done a good enough job experimentally, n's going to be really large. It would be an absolute miracle if your experiments had worked out exactly perfectly that this thing was going to have a solution, right? Because it's got way more equations and variables. So almost surely this thing is not going to have a solution, even though you're probably right. So what do you want to do? You don't want to find A's and B's that actually make this thing work perfectly. You just want to find A's and B's that make this thing work with the least error. So if you stare at this, right, you're given the x1s and the x2s and the y1s and the y2s and stuff. That's just your data. You're trying to find A and B. This is just a linear system for A and B. So you can write it in matrix form like this. This is the thing you're trying to solve. This is your coefficient matrix. This is your right-hand side. Right? So the y's, the things you measure, they always give you your right-hand side vector. And for these linear fits, why is your coefficient matrix this? Well, because the ones here just correspond to taking the 0th powers of all of your x's. And then the x's correspond to taking the first powers. Okay? So that's purely just because we're trying to fit to a straight line. So we've got a bunch of 0th powers and a bunch of first powers. But if you're doing fits to lines, that's what your coefficient matrix is going to look like. So we want to find a least squared solution to mv equals y. And we know that least squared solutions to mv equals y are just real solutions to the normal equations. Okay? So you now just take your data matrix. Well, m consists of your, not all of your data, not the measurements, but the parameters that you control, those values. You take that, multiply it by m transpose, you multiply your measured vector by m transpose, you get this normal system, and now you just chuck this into Mathematica and ask it to solve that system for you, and you know it's going to have a solution because it's a normal equation. Okay, it's always consistent. And what's even better, right? We know that the corresponding normal equation is going to have a unique solution if and only if the columns of m are independent, right? The only possible way the columns of m wouldn't be independent is if you chose all of the x's to be equal, right? And if you're trying to fit a straight line to understand how temperature affects pressure, and you took all your measurements when the temperature was 7, that wouldn't make very much sense, right? You're trying to fit a straight line through one data point. So as long as you don't do something completely ludicrous, like pick all of the x's to be equal, you get a unique solution out of this. Okay? So this is really no loss of generality to assuming you get a unique solution. You would only not get a unique solution if you did something very strange. Okay, so let's find the line of best fit for this data. So the y vector is all of these values, right? The measured values. So y is 2, 3, 7, 12. And what's m? M is 0th powers of all of the control variables. So 1, 1, 1, 1. There's 4 data points, so I'm going to get 4 rows. And then the first powers of them. So 0, 1, 3, 6. All right, that's my m. Now it's just a question of doing some first year stuff. So your m transpose m, in this case, is then 4, 10, 10, 46, which is symmetric, which it should be. And m transpose y is 2496. And if you go and solve the corresponding normal equations, that's m transpose m, v equals m transpose y. What do you find? You find that 4, 10, 10, 46 augmented with 2496 gives you 4, 10, 0, 21, 24, 36. And so V2 is 12 on 7, and V1 is 12 on 7. Now, in general, A and B don't have to be equal at all. This is just a fluke. So the line of best fit to your data is y equals, now we put V1 as the constant, and we put V2 as the coefficient of x. Okay, so that's our line of best fit. And if you draw these data points in Mathematica and you draw a line through it, this line, that'll be reasonable, right? It'll sort of do a reasonable job of piercing the middle of your data cloud. Okay. So you can generalize the heck out of this. Okay, so one way you can start generalizing this is to say, all right, I don't think my data is well described by a line. Maybe it's well described by a quadratic or a cubic or a quartic or any polynomial that you like, right? And then you just play a slightly more complicated game, right? You still take your measurements, right? You measure for each different temperature value, you measure the pressure. And then you don't stick those data points into the equation for a line. You stick it into the equation for whatever degree polynomial you're interested in. Okay? So there's some arbitrary coefficient sitting in front of the constant, another coefficient sitting in front of x, another coefficient sitting in front of x squared, blah, 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 some coefficient sitting in front of x to the m, if m is the degree you think your polynomial should have. So you fit in all the x1s into this one with y1, stick all the x2s into this one with y2, etc. Play the same game. You get a slightly more complicated m, right? You've got the 0th powers in the first column, you've got the first powers in the second column, and then instead of stopping, you've got the second powers in the next column, blah, 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 up to the nth powers. But then you play exactly the same game, right? So we want to find this vector, we want to solve it by doing, we want to find the least squared solution, so we solve the normal equations. So solving m transpose m v equals m transpose y gives us v equals 2, 5, minus 3. So the best fit quadratic is y equals 2 plus 5x minus 3x squared. Yeah.
Sorry, where'd you get the v from?
The v.
Like the 2, 5, negative 3. That from the last example.
So this is just solving this. So you stick all of that, you solve that's your m, so you can get m transpose m, right? I'm solving this new system for v. It's not from the previous example. This is just, I've got, sorry, I told you this one. It's this data. So you stick that point, those points in. Yeah, otherwise this wouldn't make very much sense. So we got this collection of data. I could have actually used the previous data. So you stick, that's your data, right? And you stick it in and you get that. Okay, so you can play this game with not just with polynomials, but if you think your data is described by some linear combination of sine and cosine and exponentials and logarithms, whatever you like, you can use it for any linear combination of any class of functions you like, right? And find the coefficients by doing this least squared business. Okay, so that is, I think, enough for today. I'm going to skip linear regression, and we'll start chapter 8 next week. Okay?